In modern electronics, sensors act like the senses of a device, enabling it to perceive the surrounding environment. They convert physical information such as light, heat, and distance into electrical signals, allowing machines to see, feel, and hear. Among many types of sensors, the photoresistor is one of the simplest yet most practical components for detecting light. It is commonly used in night lights, light-controlled switches, and automatic brightness adjustment systems. A photoresistor is a passive electronic component whose resistance changes based on the intensity of light. Its core consists of a layer of light-sensitive semiconductor material. When light hits the surface, more electrons are released, reducing its resistance. To quantify light intensity, we typically use two units. Lumen measures the total brightness of a light source. Lux indicates the illuminance, that is, the amount of light received per square meter. The behavior of a photoresistor is intuitive. The stronger the light, the lower the resistance. The weaker the light, the higher the resistance. This property makes it ideal for applications like lights on when dark, lights off when bright. In practical use, a photoresistor needs to be connected to an Arduino analog pin to read its variations. However, since it has high impedance, connecting it directly to an analog pin would result in little to no voltage change. Therefore, it must be connected in series with a fixed resistor to form a voltage divider circuit. This way, changes in light intensity are converted into voltage changes, which can then be read using analog read. A voltage divider is a simple circuit used to proportionally reduce an input voltage to the desired output voltage. It consists of two resistors connected in series, utilizing the principle of voltage division to achieve voltage reduction. The basic principle of a voltage divider is based on Ohm's law and the voltage distribution characteristics of series resistors. When two resistors, R1 and R2, are connected in series, the input voltage VAN is distributed across the resistors according to their resistance values. The output voltage VOUT is taken across R2. The voltage divider formula is Vout equals V in multiplied by R2 divided by R1 plus R2. Substituting Vin equals 5 volts and Vout equals 3.3 volts into the formula, we get R1 equals 1.7 times R2. If R2 is chosen as 10,000 ohms, then R1 is 17,000 ohms. After completing the wiring, we need to upload the corresponding code to the Arduino. In this code, we read the analog value of the photoresistor through pin A0 and print its changes in real time via the serial monitor, which can be used for debugging or controlling other devices. In previous experiments, we often used the delay function to control time intervals. However, delay blocks the entire program, making it unable to respond to external events such as button presses or sensor inputs. In such cases, we can use the more flexible millis function. Millis returns the total milliseconds elapsed since the Arduino started running. We can use this value to manually control timing logic without pausing the program. This program implements a non-blocking LED blinking function, allowing the serial communication to continue working without being paused by delay. It is one of the foundational techniques for multitasking. In this lesson, we learned the working principle of the photoresistor and its connection in a circuit, mastering the method of reading light intensity changes using a voltage divider. Additionally, we introduced the millis function to achieve non-blocking timing control. In the next lesson, we will delve into line detection, autonomous control systems, and their debugging methods, further enhancing the system's intelligence and responsiveness.